Hello, welcome to our next set of notes. We're on section 7B. We're actually split 7B into two parts, so that's why this is part one. We only cover 4 sections in this unit, but we decided to take our time and slow down a little bit with 7B. So we're going to keep finding probabilities. That was what we were doing in 7A. And we learned about the theoretical method of finding probabilities where we looked at the number of good options over the number of total possible options, we're counting those outcomes for a specific event. And we want to do that today still, but we're actually going to look specifically at times when you might have multiple parts to your event or multiple events. A lot of times this happens like when you go to play cards, you don't just draw one card, you draw multiple cards. When you roll a die, you usually roll several dice. You play Yahtzee, you roll 5 of them. You might flip a coin multiple times. You don't just flip one. So we have these times where we're looking for multiple things to happen. If I'm playing poker, I might want 2 of the same card, to work on towards getting my flush or my straight, or my 4 of a kind or something like that. So I want 2 of the same matching card. If you're rolling dice, playing Yahtzee, you want multiples of the same number. So that's something that happens all the time is we're looking for more than one of the same thing or even specific things that might be different. I'm looking at the, we talked about a litter puppy last time. Maybe I want to get a white puppy and a black puppy. I want those 2. I don't want to have a brown puppy with this litter. I'm looking for those colors or something. So we're going to deal with situations where we have multiple things happening and we want each one to come out a certain way. Now, these fall into 2 main categories, independent and dependent. So coin tosses, rolling dice, drawing a card from a deck if you replace after each draw, these are called independent events. Now, if you draw a card without replacing it, so you pull out, each card, just without putting them one back, you pull a handful of marbles from a bag all at the same time. If I'm choosing 2 different students from a roster for helping with the project or something like that, these would be dependent events. What's the difference between independent and dependent? Well, independent events, each part has no effect on the probability of the other parts. That's the big important part of independent. So independent events are independent if they have no effect on the probability of the other parts. So you roll the die, the first roll is not going to affect at all what you get the second roll. Doesn't matter if I got a 1 or a 6 the first roll, either way my chances of getting a 5 the next roll, still the same as it was. It does not get changed. You flip a coin the first time, the next flip, you still have 50-50 heads, tails. Doesn't matter what you got on the first 20 flips, the next flip is always going to be 50-50 chance when you flip a coin. So that's independent. Independent, the first thing has no effect on the probability of the next part. There's a lot of things are independent, like we mentioned, coins, dice, even drawing cards, as long as you put the card back before you do the next draw. Dependent, the first does affect the next. So dependent events are when one event does affect the probability of another event. So this is when you draw a card from the deck and you don't put it back. If you pull out the Jack of Spades, the next card has different chances because now there's less cards in the deck. You just took the Jack of Spades out. If you're looking for a jack, there's less jacks in the deck, which means you actually have worse chances. Or if you're looking for like a queen, not a jack for the second one, you actually have better chances because you pull the jack out. Now there's less cards, so there's more queens per total. So you change the probability. So anytime where you change the probability with the first action, that's dependent events, where one thing affects the probability of the next. So a big part of this section is being able to identify things that are independent versus dependent. One thing that's nice is coin flips and dice rolls pretty much always independent. So if I say, oh, you flip a coin 5 times in a row, well, that's definitely going to be independent. Because every time you flip a coin, it does not affect the next flip. The first one heads, well, I still have 50-50 chance of heads on the next one. It doesn't matter what I got the first time. So this is definitely independent. Coin flips, they don't change the probability. The probability does not change. Drawing a card from a deck, burning the card, and then drawing another card. Because the first card was burned, it wasn't put back, it's changed the probability. There's less cards in the deck. That changes the chances of getting any specific card. So because we destroyed the card, we didn't put it back. There's no replacement. That's a really important word here. When you deal with a deck of cards or anything where you're pulling stuff out, if you don't put it back in, if you keep it out before you do the next draw, that's going to be dependent. So this is dependent. So look for that keyword. Anytime you see no replacement, you're not putting it back, it's being burned, it's being kept, it's not being put back, that tells you that, oh, this is dependent because it's no replacement. Bingo caller draws A4 and then he draws A3. Well, he doesn't call A4 again, right? When you call bingo, you don't call the same letter over and over again. You call it once, and then you move on. You call the rest, and you keep going until someone gets a bingo. So because the A4 isn't going to be used again, once that one's pulled out, the chances are different now for getting A3. Because before there was more balls in there that you could pull and get your number. Now there's less, so we've changed the probability. It's actually more likely A3 than it was before you drew A4. So this is dependent. And again, it's because A4 can't be called twice. So we've changed the number of options there are. We removed one. Just like when you pull a card out, don't replace it. We didn't put A4 back in the mix. Blackjack dealer deals you a king of spades and then a two of hearts. So this one, he's pulling both cards out. He didn't put the king of spades back in. There's no replacement. So again, it's dependent. There's a lot of dependent things because these things like playing cards and stuff, you're pulling stuff out and you're not putting it back, you're changing the number of values. So this is dependent. Roll a pair of six-sided die, even though you're rolling them at the same time, it doesn't matter because each die is doing its own thing. One does not affect the other. Yeah, I know the dice might bump, but it's not really changing the theoretical probability or anything. So one die is not affecting the other. You just roll each die. Even if you roll the same die over and over again, each roll is not being affected by previous rolls, so this is definitely independent. Again, coin flips, dice rolls, those are typically independent. And the way to make card drawing independent is to have replacement. But if the card's not replaced, then it's dependent if it's not replaced. So this one, versus six-sided dice, it's independent. They do not affect each other. The probability changes for one versus the other. Okay, why is that so important? Because the way you calculate the probabilities for these kind of combined events is going to depend on which one you're doing. There's a different method for independent and dependent. There's a different formula. They're very much related. They're similar. You'll see how they really look similar in some ways. But you have to determine which one you're doing and then calculate the correct way. So let's start off with independent because independent is actually the easier one. So we're going to start off and look at probabilities for independent events. We call these AND probabilities. It's AND because you have to get this and you have to get that. You have two different events. You want both of them to come out a certain way. And that's why it's called AND probability. You want this and that. So when you're computing probability for independent events, you calculate probability for each event and then multiply those probabilities together. That's the way you do it for AND events. So if I find the probability of A and B, then I find the probability of A, find the probability of B, and then just multiply those together. That's the method. For independent, it's pretty straightforward. Just find each and multiply. This is a formula that's on your formula sheet. You'll see there's a decent number of formulas on this formula sheet. So I'm not expecting you to have these all memorized, but it is important to know when you use this. A lot of times on the test, I have people try to use this at the wrong time or not using it what they should. So just be aware, be ready to use this formula and know it's anytime you're trying to do two things and you need them both to come out a certain way. You want them both to come out right. For example, you flip a coin twice, you're trying to get heads both times. So this is because I'm flipping it twice, not just flipping it one time. I'm actually doing two things. I'm doing probability of getting heads the first flip and heads the second flip. They don't say and on here, and don't give away that obvious, but if you're trying to get both heads, that's the same thing as heads and heads. You want both of them heads. And again, to find that probability, I just have to find the probability of heads for the first flip, probability of heads for the second flip. And because they're independent, they don't affect each other. I can just find those separately and then just multiply those together. Of course, heads is pretty easy because heads, there's only one good option, heads, out of the two sides of your coin. So 1/2 is the probability of getting heads. And that doesn't change because they don't affect each other. So every time there's a 1/2 chance of getting heads, so you just multiply those together And you see you actually have a 1/4 chance of getting heads twice, right? Getting heads and heads. So 1/4 is the chance of getting heads both times, 2 in a row. Try it with a die. You roll a 6-sided die, you roll an odd, you roll a 6 and then an odd on a 6-sided die. So you're trying to get a 6 and then an odd. So we're trying to do both. Again, and probably have to have two things. You have to be doing both of them. So I'm doing a 6 and I'm doing an odd. Those are the two results I want. I want a 6 on the first roll, I want an odd on the second roll. So again, because it's independent, rolling the dice, they're not affecting each other. We're not, changing the odds. When you roll the dice the second time, it doesn't change the probability. So we're going to just find the probability of getting 6 the first time, find the probability of getting odd the second time. I'll just multiply this. Chance of getting 6, you get 1/6 out of the 6 sides of a die. So there's 1 out of 6. 6 sides on a 6-sided die, and we're just trying to get 6, trying to get one of those 6 sides. Second time, I'm trying to get an odd, which would be like 3, 5, and 1, 3, and 5. 1, 3, and 5 would be 3 good choices. So I have 3 out of 6. I'm going to multiply those guys. You could simplify before you multiply. If you don't want to multiply 1, 6, 3, 6, and then have to simplify, you actually make your life a little bit easier by simplifying this fraction first. These both divide by 3. Here you get 1, you get 2, so it's actually 1/2. Half the sides are odd. And that way when you multiply, remember when you multiply straight across. I did like 2 times 2 gives me 4 up here. I do 6 times 2, I get 12 on the bottom. 1 times 1, I get 1 on the top. If you'd done, 1 6 times 3 6, you would get like 336, but that would simplify to 112. That's the idea. You'll notice these probabilities are pretty small, right? We went from like halves and 6 to like 4ths and 12ths. It's getting smaller because it is harder to have 2 things come out the way you wanted than just one. It's easier just to roll a 6 on a die than it is to try and get a 6 and to get this other thing as well. I'm trying to do something more complex. It's less likely to happen. That's why the probability is lower. So the and probabilities tend to be small. Trying to get multiple things to happen is usually difficult. Okay, let's try one more. Let's draw a card. Remember, with drawing cards, it's only independent if you replace the card. So this right here is really important. They're putting the card back. If it said they kept the card out or they didn't replace the card, then we would have to do this with a different method. We can't use independent, but because of replacing the card each time, that's what makes this work. So we replace the card each time. So we're going to play poker, we're going to draw a heart. So we're going to draw a heart. We're going to put a card back. So the full set's in there, we can draw again. And now we're looking for a 5 of spades. So probability, I'm going to just put a heart because you guys know that's the heart symbol. So when I get a heart first, and then I want to get the 5 of spades. I'm not going to try to draw a spade, so I'll just put 5 of spades. Okay, so those are the 2 things I want. And again, the way to do this is I want both things. I'm going to find the probability of a heart first, and then I'm going to multiply that with the probability of getting the 5 of spades. What I want. Hearts, there are 13 hearts. Remember in the deck there are 4 suits, and in each suit there are 13 cards, so there are 13 hearts. 2 through 10, Jack, Queen, King, Ace. So 13 hearts. And remember that the standard deck has 52 cards in the standard deck. So we're assuming this is standard deck because they didn't say otherwise. So we'll say 13 out of 52. 5 of spades, there's only 1 5 of spades out of the whole deck, and then out of the whole deck of 52 cards. We put the heart back in after we drew it, so there's still a full deck to draw from. That's why there's 1 out of 52, and that's what we multiply. Stuff like this, if you don't want to simplify this by hand, I understand. You can kind of make your calculator do it. Should use my T30. So you can type this in. You can actually make it do the multiplication as well. You can type in the multiplication problem. So I would do 13 divided by 52. And then I'd multiply that times, I don't know why, I guess I could do the fraction button. Let's do the fraction button instead. I'm going to do 13 fraction button 52. And then get out of that times 1 fraction 52. And the nice thing about the fraction button is it does nicely simplify it for you. So it's 1 over 208, 208, and that is simplified already. It's 1 over 208. If you had used the fraction button, or maybe you have a T84, typed it with divisions, it might look like this. So you do 13 divided by 52, and you multiply that by 1 divided by 52. and you get a decimal, but you can hit the math button, turn it back, and go fraction, and it'd still be 1 over 208. So that's something you could do. Again, these should be simplified. Every once in a while, my math lab will ask for you to give it in decimal form, so you would just actually divide out and give the decimal. So like you give the 0.0048 on this one, and round it as they tell you to. But I'm going to mostly stick with fractions because they're exact. The decimal's always rounded. But just watch. Sometimes my math will watch with decimal. Now, this whole independent probability doesn't just work for two things. You can actually build it up and use it for like multiples. So you want to do 3 or more events. It still works. You just, for example, here, if I have 3 events, A, B, C, you just multiply all the events. So the more events you have, the more parts you can just multiply. So if I'm playing a poker game where I draw 5 cards, and I'm looking for a specific hand, this, and this, and I just say probably each one of those cards, and then multiply. Of course, that would be a bad example because that would be independent. I have to be like putting the card back each time, which isn't what you do in poker. But if I'm trying to roll the dice 5 times, or anything like that, I just have to do each probability for each part and multiply them all together. So the big thing is, you're trying to do multiple things and you want them all to come out a certain way. That's and probability. If it's independent, you just find the probability of each one, multiply them all together. So let's say I want to roll a 6-sided die 3 times. I'm trying to get an even all 3 times. So 6-sided die, I'm rolling and trying to get evens. So I'm doing the probability of getting an even the first try, and an even the second try, and even the third try, right? It didn't say even, but even all 3 times. That's what that means, right? Even, and even. I need all 3 evens. Again, what I'm going to do, I'm just going to find the probability of each one. So probability of even each time, and then just multiply those together. And this stuff like this, it really works nice because once you know the probability of even, since it doesn't change, right? The dice doesn't change after each roll. Then you just know it's the same for all 3. Probability of even, well, there's 3 evens out of 6 sides, so 3, 6. We all know that 3, 6 is the same thing as 1/2. So I could even simplify that right away and just say, okay, 1/2 is a chance of getting even, and that could be true for all 3 steps. So I just do 1/2 times 1/2 times 1/2 and get 1/8. And that's my chances of getting 3 evens. Just 1/8. So now you can find the probability. What if I want to roll 3 times to get an odd? Well, you do the same thing, just do it for odds, or give a specific number. You just find the probability of each event and multiply them together. So that's independent. That's the easier of the two because each probability is pretty straightforward. The other probabilities don't affect it. That's how that works. Now we want to step into next going to dependent. But before I can get really into like just the formula and calculate dependent, we talk about what's called given probabilities. So with dependent probabilities, the second probability will depend on what happens on the first probability. We call that a given probability. So when dealing with multiple events, it's necessary to calculate the probability of an event after a previous event has already occurred. So something already happened, changing the probability. So this is called a given probability. And a given probability, we write that as P of B given A. So we're looking at, okay, find the probability of B given A already happened. And A is going to change B. For example, if you're playing blackjack, you might want to know your chances of getting dealt an ace after the first card you got was a jack. So again, when they pulled that jack out and gave it to you, that changed what was in the deck. There's not a full 52 cards anymore, there's 51. There's not as many jacks in the deck. There's still 4 aces. So now when you do your probability, though, you have to account for that. You have to think, okay, well, there's four aces still, but there's only 51 cards left. The probability has changed. It's not the same as it used to be. So that's the idea. So given probability is saying, okay, something happened. Now let's look at what the probability would be. So for example, you're dealt a 7 after receiving a jack from a standard deck of cards. We're trying to find the probability of getting that 7 given you already received the jack. That's the probability. So when you do a given probability, you have to think, okay, what are the chances? Well, you assume the first thing was successful. They gave you a jack. That thing happened. So you got a jack. And then you think about how the chances are changing. Well, pulling out a jack out of the deck still leaves the 4 sevens. So there's still 4 sevens because there's none of the sevens have been removed. But instead of 52 cards now, because a jack has been pulled, now there's only 51 cards. So the given probability is different than just finding, P of 7. If I just did P of 7 by itself, it would have been 4 out of 52. Because that's how many, if you just drew the 7 first, it would be 4 cards out of 52. But the given probability, we're saying, okay, we already got the jack out, says, oh, what's different now is there's less cards. There's only 51 because the jack got pulled. There's still 4 sevens, so we didn't pull the 7, we pulled the jack. If this had been like 7 given 7, then you would have less 7s because we pulled a 7. But here we pulled the jack, leaving all 4 sevens, but there's now only 51 cards. So this would be your answer. I don't believe that one simplifies it all. You can double check with your calculator, but for tips you want to have a common factor, so I want to simplify. Okay, after you pull a green marble out of a bag that had 5 greens and 4 blue marbles, you want to know the probability of pulling out a second green marble. So you start out with 5 green and 4 blue, and you pulled out a green first, but now you want to find a second green. So we're looking for another green. So we're going to do green given we already pulled a green the first time. So green given green. Okay, so we're looking for green. So right now we already know that the first pull took one of these greens away. So that first, drawing, mulling a marble out, we took away one of the greens. So now there's only 4 green marbles left because they took one out. When you're trying to do for the same thing twice, you have to account for the fact the top's going to change because you pulled, that number out. Also, the total here to start with was 9, but they pulled a green marble out, so now there's only 8 marbles left. So even though the first green, there was 5 out of 9 were green to start with, that's a little bit better than half. Now, because you pulled a green out, your chances are lower to get a green the second time because there's less green marbles in this bag of marbles. I would simplify that down to 1/2, because 4 and 8 divided by 2, or divided by 4. Divided by 4 is 1, 8 divided by 4 is 2. That's our chances of our second green marble. Once you pulled out that first green marble, reducing the number of marbles, that's what would happen. Say you randomly choose a weekday to order takeout, but not Friday because you have company. So we're going to be probably picking Tuesday. So Tuesday, given that we already used up Friday for something else. So we're not going to do Friday. So idea here, we're saying weekday is going to be, Monday through Friday. So that's going to be 5 days. And we're picking Tuesday. Well, Tuesday, there's only one Tuesday out of the 5 days of the week. And there were 5 days, but we already used Friday. So Fridays we're already busy. So we actually are down to just 4 possible days. So because one of the days was taken, instead of a 1 in 5 chance of picking Tuesday, we have a 1 in 4 chance of picking Tuesday. That is how given probabilities work. They're not a big deal. I know I make a big deal, spend a whole page on them. But if you think about it, really it just makes sense. You're just thinking, okay, you do one thing, now the counts change. Instead of this many options, now there's this many options. You'll notice the bottom always decreases because you have less options. You go from 52 cards to 51 cards. You go from 9 marbles to 8 marbles, 5 days a week to 4 days a week. That's always going to happen. The bottom's always going to be changing because you're taking stuff out of the mix. The top can change sometimes. It can sometimes not. Like when we were doing green marbles twice, we saw the top number changed. Went from 5 green marbles to 4 green marbles. That can happen. But if you try to pick something different than what you already picked, a lot of times the top won't change. There's one Tuesday no matter what. Picking Friday didn't change how many Tuesdays there were. So that didn't change. We'll use this to do dependent probabilities. So with dependent probabilities, we're going to do 2 steps just like we did with independent. We're going to multiply just like with independent. But the difference is we have to worry about how that first step is going to change the probability for the second step. So the formula for dependent probability, so when you're going to dependent, where one depends on the other, it's the same thing. We say find probability of A and B, find the probability of A times the probability of B, but the big difference here is now you have to worry about that given A. That's the only difference in the formula. Otherwise, it's the same formula. It just says, oh, that second step, you have to think about what happened on the first step, how that first step kind of changes the probability because they're dependent on each other. The first one affects the second one. So that's the only difference. And probabilities are always multiplication. You're always going to multiply to find and probabilities. We want this and this. So like I want to draw a queen and I want to draw a jack. I want 2 things to happen. So I'm drawing, I'm finding the probability of a queen and a jack because I'm not replacing it. So there's no replacement. If they had said something about putting it back after each draw, then I'd have to say, okay, that's independent, but because there's no replacement, it's anything but putting it back. This is dependent. To do dependent, I still find the probability of queen. So that first draw, I need to get a queen. and it's the beginning, so it's just whatever chances are of getting a queen, that's what it is. But the second draw, I say, okay, now I find the probability of getting that jack, but I have to remember I pulled out a queen. So I'm going to say a jack given I already got the queen. I'm always going to assume that the first one's successful. I'm not going to just try and guess like what happened. Well, no, I'm going to assume this is successful. So if I didn't get the queen, then why even bother on the second half? Right? I'm trying to get both. I want to get a queen and a jack. I want both parts. So I have to assume this one's successful and then say, if you got the queen, now what are your chances of getting the jack? And I multiply those together. Okay, remember a standard deck, 52 cards. There are 4 queens in that deck. So first off, I have 4 out of 52 are my chances. So there's 4 queens out of that 52 card deck. At the very beginning, I haven't taken anything out yet, so I'm looking for that first queen. There's 4 out of 52 chances. Then I say, okay, now find the probability of getting the jack, but I have to assume I pulled a queen out. I didn't pull all the queens, right? I just drew 1 card. I got a queen. So I pulled 1 queen out, so now there's less queens. But I'm not trying to get a queen, I'm trying to get a jack. So I'm going to do 4 because there's still 4 jacks. But now I'm going to do out of 51 cards because I pulled one of those queens out. So the first draw, I drew a queen, and now there's only 3 queens left. But I'm trying to get jacks. So I'm going to pull one of the 4 jacks, and again there's 51 cards to pull that out of, and I multiply those together to get my answer. You could multiply as is. I definitely think it'd be easier to simplify it a little bit. Like you can divide this by 4, get 1, and this by 4, get 13. Sadly, I think that's the only simplifying you can do on this one. So you do end up with like 4 on the top and 13 times 51 on the bottom. So 13 times 51 gives you 663. If you're not sure, you could just do all the work in the calculator. You do 4 divided by 52 times 4 divided by 51. And you should get the same thing after you use the math fraction button to turn it into a fraction. 4 out of 663. And again, that's the same as 0.006 rounded. If you're okay with rounding. Most of the time, I prefer the fraction because that's a little bit better answer. That's what I'd be looking for. And that's my math. I'm most of the time looking for the fraction. Sometimes I want the decimal. Okay, so the big thing here is dependent. We didn't put cards back after each draw, so we had to worry about how the probability changes. There's less cards each time you pull. So each time you pull, you have less cards. The jacks didn't change because the first pull was a queen, but the number of cards changed. There was still a total was less, and that's why that fraction changes. Try another one. You draw from a bag containing 6 blue marbles and 7 red marbles, and you're drawing 2 blues. So you reach in the marble, you pull out 2 blue marbles. So this probability, we're looking at the probability of getting a blue and a blue. Right? We're trying to get 2 blues. We want both blue. Again, this is dependent because if you pull a blue marble out, there's less marbles in the bag. So to find the probability, we're going to have to think about this as kind of in 2 steps. Even if you reach in the bag and grab them both at the same time, we'll kind of pretend, think about like what happens. And think about how you pull out the first blue marble and how that changes. The chances of the second one being blue are different. We can do it that way, even though we pull them both at the same time. So what we do here, we say find the probability of the first one being blue. That one is the first step, so we just do it by itself. When we go to do the second step, we're going to say probability of getting a blue. We're going to say given there was a blue pulled already. So we're finding the probability of getting a blue once you already pulled the blue out. That's what we're doing. Okay. First blue, there are 6 blue marbles to pull from. And out of this bag here, they don't tell us the total, and they'll do that a lot. They'll just tell you the different numbers. You should be able to add those up and get the total. 6 plus 7 gives us 13 total. So 6 out of the 13 are blue. That's our first chance in the first marble. We go to draw the second blue. Well, now there's less blue marbles, right? We drew a blue out already, so now there's only 5 blues left because we pulled the blue out in the first step. This one should decrease if you're doing the same color over again. Same thing over again. The bottom always decreases because you take from the total. So we pull the blue marble out, now there's only 12 marbles left. That is how it works. So 6/13, 5/12, and we'd simplify that. This one, if you get, 30 over 156, I believe. I guess I gotta double check myself. 13 times 12 is 156. Yep, it is. And then that one actually does simplify. If I want to simplify 30 over 156, hit the math button, turn it into a fraction, you actually get 5 over 26. Would be the simplified version. Again, my math app's going to be pretty good. They want you simplified fractions. They don't whole number. Same thing on the test. I would ask for a simplified fraction because you can make the calculator do that. The big thing I'm really worried though is, do you know that when you have no replacement, you're not putting marbles back in the bag, you should do two at the same time, that you need to do dependent probability. That the second fraction is going to change because you didn't replace the marble. That's what I'm really worried about. Do you know that? Do you know that you have to do the probability differently when you're not putting it back in, when every time you draw it, there's less marbles left? Okay, one more. Blackjack dealer deals you a jack and then an ace of clubs. You're trying to get a jack, ace of clubs. There's no replacement. Right? This is what's important here, is there's no replacement. I'll be pretty obvious on the test. I'll mention that there's replacement or not replacement, so you'll know if it's dependent or independent. Again, no replacement means that it's dependent, and you have to worry about how things change. So we're trying to find the probability of getting a jack, and then ace of clubs. And we'll try and draw a club. So we'll just do ace of clubs like that. So first off, I'm going to find the probability of a jack. No problem. Not a big deal because it's just a jack by itself. I can't even do that right now. Okay, there's 4 jacks. Standard deck has 52 cards. Then I want to do the probability of an ace of clubs. Given we already drew a jack. Again, we're thinking about how the probability is changing. So now instead of just saying I'm doing an ace of clubs out of the whole deck, well, I drew a jack out. So now there's only 51 cards left. Ace of clubs, there is only one ace of clubs, so there's only one option for that, one good option, which is the ace of clubs. And that's the change. That's the dependent probability. We're saying, okay, the 51's changed because there's one less jack because we pulled the jack out in the first step. That's what I would multiply. This one does simplify. I'm going to divide this by 4, get 1, divide this by 4, get 13. Just to make this a little bit simpler, 1 times 1 is 1 on the top, so I really just have to multiply the bottom. 13 times 51. And you get 663 again, like we saw earlier. That's our answer. Again, you see these and probabilities, a lot of them are really small answers, right? It's really hard to get specifically a jack and an ace of clubs. Even the ace of clubs by itself, you only have a 1 in 51 chance. We're trying to draw 2 cards and get both a jack and an ace of clubs. That's pretty low chances. Not very likely. It's hard to do. Okay. Now we mentioned before with the independent, you could combine that and you can do like more than just 2. So you can keep like doing it over and over again. And that's true for dependent as well. You know, a lot of times you play cards, you'll draw more than just 2 cards. You know, if you're playing poker or something, you might draw 5 or 7. What kind of poker game you're playing. So this whole dependent probability formula actually does expand, and it goes as big as you want. If you're trying to find 3 things, for example, you find the probability of the first one, and then just like before we were doing, you find the probability of the second one, given the first. But when you go to the next step, now you have to think about trying to find the probability based on the first 2 things already happened. So when you go draw that third card, well, now you've already removed 2 cards from the deck, and each card you pull out of the deck is changing the probability. Every marble you pull out of the deck is changing the probability. So you have to account for all the changes you've made up until that point. And that's what's going to happen. The more steps you do, the more you have to worry about all those givens that have happened, all the things that have changed it. So we'll do a couple examples of this, you know, with more than just 2, with 3 or more, and we'll see how that works. So there are 5 students passing and 2 students failing a course. So 5 passing, 2 failing. What is the probability that 3 students chosen at random will be passing? So I'm trying to find the probability I'm going to get a passing, and a passing, and a passing, right? I want all 3 to be passing. But it's dependent, because I'm not going to pick the same student twice, you know, so no, you know, repeat. I can't pick the same person over and over again. I'm not putting them back in the mix to pick them again, so no repeats. So then I would say, okay, first one, probably of passing. So I'm thinking of over this, you know, this group, what's the chance I pull someone that's passing? Well, there's 5 students passing out of, what, 7 students total, right? 5 passing, 2 failing, so there's 7 students total. For the first chance, I have 5 out of 7. Then I'm going to multiply that by the chance of getting someone passing, given I already picked someone passing. So I already picked one of the passing students. So now there's only 4 passing students left, because I already picked one of those 5. And there's only 6 students left. So I changed the probability a little bit. Then I do the next one. I want to get the 3rd student passing. But now I'm doing it given passing, passing. I picked 2 students passing. I picked a passing student, picked a passing student. I'm trying to pick a 3rd passing student. Well, now instead of having 5 to choose from, I already took 2 out. I only have 3 students left to pick from. They're passing. And Between those 3 passing and the 2 failing, I have only 5 students left. You'll notice each time the bottom number goes down by 1. That's always going to happen because you're just picking 1 out each time. And here the top number is going down by 1 each time because I'm picking that same thing over and over again. If I'd switched into passing and failing, this might change in different ways. But because I'm trying to pick the same thing over and over again, this is just going down 1 each time on the top as well. And that's what I multiply. I just multiply all 3 fractions to get my answer. Again, if you don't want to do it by hand, you can use a calculator. The TI-30 really makes this nice for fractions. You can use the fraction button, so type 5/7, get out of it, type times 4/6, go over times 3/5, and just multiply all 3 fractions. So 5/7 times 4/6 times 3/5 equals 2/7, and that's the simplified version of the answer. There you go. So that's the chances of getting all 3 passing. It's 2/7. Let's try one more. What is the probability that you dealt 4 kings in a row? Again, standard deck, 52 cards, and there's no replacement. They didn't specifically say that, but they didn't say anything about putting cards back, so we're going to assume no replacement. Because there's 52 cards, no replacement, we're going to do dependent probabilities with no replacement, so we're going to find the probability of getting a king, and another king, and another king, and another king. So we're trying to get all 4 kings. As we do this, the first king's easy because nothing else has happened so far. The second king, we have to worry about getting that given the first king. The third king, now I have to worry about the fact that we've got given, king and a king already. And the fourth king, you have to worry about all the kings that happened so far. Each time we have to worry about all the put 3 kings. Because we already drew 3 kings. So each time we do, we have to worry about all the previous draws. So the first king, out of our deck, we have 4 kings out of 52 cards. Not a big deal. The next one, we want to draw a king, but we've already drawn one of the kings. So now there's only 3 kings left out of 51 cards left. Because again, we moved one of the cards, which is a king. That's why both of these have gone down. The next one, now there's 2 kings left because we drew 2 kings out of the 50 cards left because we pulled out 2 cards. And then the last one, now there's only 1 king left because we drew the first 3 kings. There's only 4 kings in the deck, and this is now out of 49 cards. This is the reason why when you're playing poker and someone gets 4 of a kind, it's a really big deal because it's really hard to do because each time you draw the next king, it's just even less chances of getting that same card over and over again. Okay, let's multiply this out. Again, I'll use the TI-30. It's a little bit nicer for these fraction things. Again, you can do the same thing on the TI-84. You just have to use the math fraction one. But I'm going to go ahead and use the fraction one here. So I'm going to do 4 out of 52 times 3 out of 51 times 2 out of 50 times 1 out of 49. And I get a decimal because this calculator doesn't even like to keep this one as a fraction. So this one would probably be one where my math I would tell you to do a decimal. 0, 5 zeros. Yeah, really slim chances. 3, 6, 9, 4. If you wanted to simplify this a little bit, we could actually find the fraction. I'm going to go ahead and show you the fraction just because it's kind of crazy. So this becomes 1 out of 13. It's 51 divided by 51 divided by 3. Yeah, so this would become 1 in 17. This would be 1 in 25. So the fraction version of this answer, you get 1 on the top, and on the bottom you get 13 times 17 times 25 times 49. So it's actually 1 over 2,707.25. So that's actually 1 in 270,000. This would be the fraction version of the answer. On a problem like this one on the test, I would totally be okay with the decimal. You can see why the decimal would be easier. If the calculator spits out a decimal, that's definitely the easier way to do it. When you're typing it out, I'm not going to expect you to maybe do it by hand like I did. Same thing on the test. If it's a decimal answer is easier than a fraction, that's probably going to be fine. I'm not going to be really picky about which one you do the decimal versus the fraction. Yeah, the decimal's a little bit rounded, but I'm not super worried about rounding. So that's the idea. So yeah, If you're doing dependent, again, you have to think about each time, each step, if you're doing multiple steps. And that's this whole section we're doing, this first half of 7b. It's all about and probabilities where you're doing multiple steps. On the second half, what we're going to do next time, we'll see we're going to switch gears a little bit and not worry about two things happening. We're going to talk about just one thing, but having choices. But before I get there, there's one more important thing in this section, really important rule. This is called the at least one rule. This is the last part of the section. At least one rule. So a lot of times in probability, you're looking not to try and get something multiple times, but just to get it at least once. So if you get it once, if you get it twice, if you get it 3 times, you're still happy. You're just trying to get it at least one of those times. So this is true for a lot of situations like buying lottery tickets. You go buy 20 lottery tickets, you don't care if 19 are duds. If at least one of those is the winning Powerball ticket, you're super ecstatic. You're super happy, right? You have 2 of them work, that's still great because they're both yours. So it doesn't matter if you have to split it with yourself. So that's fine too. So with like lottery tickets, if you go to a casino and you're pulling the lever on the machine over and over again, you don't care if you have 20 bad pulls if the 21st is a good one. That's how that works. You're just trying to get it at least once. Any kind of game of chance where you have an opportunity for like one big payout, usually you don't care about if lots of the trials are duds as long as one of the trials is successful. So we use what's called the at least one rule. If you're trying to get this event A to happen within n trials, n is just the number of times you try. Just like when we did statistics, n was the number of experiments, the number sampled. Here, this n is going to be the number of tries, the number of times you pull the lever, number of lottery tickets you buy. And you do the formula, at least one A and n trials. What you can do is you can do 1 minus probability of not getting A to the power of n, where n is the number of times you're getting. So what we're doing here is actually calculating the probability of not winning ever. Remember we said before in last section that you can find this whole opposites probability where you subtract from like 100%. So if we find out the chances of never winning is 20%, well, the chance of winning at least once is going to be the 80%. That's why we're doing the little 1 minus part. We're trying to find the opposite. And so here, this is a chance of never winning. So not A is the chance of not winning. And if you do that over and over again, you multiply times over and over again, n times, you find the probability that you lose every single time. But when you subtract that from 1, now you've got the probability of at least one try. It's weird to think that the opposite of at least one is none. If you think about it, 1 or more, you could win 1 time, 2 times, 3 times, 4 times, up to however many times you try. That's one side. The other side is not winning at all. So it is the opposite. So this is another formula on your formula sheet, trying to find at least one trial in n trials. And I'm going to have to say something about at least one. If you see this formula in use, you're going to see something about at least one. Like here, say we want to roll a die 5 times, get at least 1, 3. So that's an at least one situation. So our probability, we're trying to find the probability of at least 1 5 in 3 tries. That's what we're trying to do. So again, 5 would be the thing we're trying to get. 3 is actually our n. It's the number of tries. The more times you roll, the bigger n would be. So we're going to do 1 minus, and we're going to find the probability of not getting a 5. We're going to do the opposite. So trying to get 5, we're going to not get a 5. And we're going to do that to the power n, which is going to be the power of 3. Well, the chance of not getting a 5 is going to be 5 out of 6, right? Because there are 5 sides of the die that are not 6s. Or sorry, not 5s. So there's 6-sided die. 5 of those are not 5s. So 1, 2, 3, 4, 6. Those are the sides that are not 5s. So I'm actually going to do 1 minus 5 6, the fraction to the 3rd power. Because every time I roll, I have a 5/6 chance of not getting it. First roll, 5/6 chance you'll get it. Second roll, 5/6 chance you'll get it. I'm actually using that independent formula because dice rolls are independent. This formula only works for independent events because you're not having to worry about the change each time. So this is for independent, like rolling dice and playing, buying lottery tickets. They're independent, and that will give me the answer. So again, we're going to find the probability of never winning. So all the rolls are not 5s. And then subtract them from 1, and we'll find the probability of at least one of them being a 5. It's okay if you get multiple 5s. If all of them 5s, that's fine. We're finding the probability of not getting it and subtracting 1, and then that'll give us at least 1. So 1 minus, I'll do parentheses to be safe. 5/6 is my fraction. Close that. Do my power button, which is a little up arrow. We saw that a lot in the first unit. And 3 is the power because that's the number of tries. So how many times you roll the dice, how many times you buy a lottery ticket past your trials. So in this case, we get 91 of 216. Now, if you get a fraction and in math that's asking for a decimal, there is a way to turn this into a decimal. On this calculator, you hit the second button, and this little F to D, it just will switch it back and forth between fraction and decimal. So you do that, and that's how you get the decimal. 0.421, we'll say 3. My math I would specify. If they want a decimal, they'll tell you what to round to. So just watch for rounding. So this would be the exact answer. This is rounded. Just watch. Are they looking for the fraction of the decimal? I would probably be fine with even on a question like this on the test. I'm not going to be too picky as long as you're doing the formula correct. That's what I'm looking for. Did you figure out what the chance of not getting a 5 are? 5, 6. Did you figure out the number of trials? Yep. And did you remember subtract from 1? That's what I would be looking for. Okay, let's do another couple, and then we'll be done. What is the probability that a student doing a multiple choice test will get at least one right answer if they have 10 questions, if each question has 4 choices? So there's at least one answer, so that's at least one right there. We're doing 10 questions, that's going to be our number of tries. Each question is a try. You have to try to get the right answer. And we're looking for at least one right out of 4 choices. So we're trying to find the probability of getting a right answer in 10 tries. So we're going to do 1 minus probability of being wrong to the 10th power. Well, in this case, because there's 4 choices, you're probably being wrong. Well, there's 3 wrong answers and 4 possible answers. So our probability of being wrong would be 3/4. So I would do 1 minus 3/4 to the 10th power. That would give you the probability of getting at least one of them right. If you get 2, you could get 3. If you get all 10 right, that'd be great. Those are options. But we're saying we want to get at least one of them right. We don't get like a perfectly 0 score. We want to get at least one right. So if I was going to do this, I'll use the other calculator just for those people that have T84 pluses. So I'm going to use this one. It's 1 minus. I'm going to type 3/4, but again, I'm going to put parentheses to be safe. I'm going to do 3 divided by 4. Close that parentheses. Do my little up arrow right here. That makes my power. Type in my 10 and hit enter. This one you can see it's actually really high, 94%. It does give you a decimal. If you're asked for a decimal, that's fine. I need to round somewhere. Let's round there. That's probably more than I need. It's about 94%, 0.94. If you want the fraction, again, that's what the math button's for. And the first option turns it back into a fraction if you hit enter twice. This one, you'll notice, doesn't, though. And that's where the TI-34 can be messed up. Maybe it's hard sometimes. In this case, you'd actually have to sit there and maybe do 3/4 to the 10th power. Figure out what that is, like 3 to the 10th, 4 to the 10th. And then that's your fraction you're subtracting from 1. So it'd be a little tricky to get this into a fraction form. That's one reason why I'm not going to be super worried about fraction form on the test. I would be fine with a decimal. I guess, let's check. Maybe the TI-30 actually goes a decimal. I don't even know. So let's try it. Let's do 1 minus fraction 3/4. Oh, I need to do that to a power of 10. I think that should just be on the 10. Nope, so yeah, this one gives me a decimal as well. So sometimes these calculators, they're just not going to do the fraction because it's more work for them to figure out the fraction and just to do the decimal. And that's why I'm not really going to worry about on the test if you give me a decimal versus a fraction most of the time. So, problem like this one, definitely decimal makes sense. And then watch my math, they'll tell you what to round to. Okay, let's try the last one. So one, I've been mentioning, games of chance, lottery, stuff like that, and that's definitely a way to use this. But another way to use this is actually to look at like safety features and stuff. So when people design stuff with fail safes, they basically design a backup. So if one thing fails, then the next thing saves it. So you might have a harness where if one strap breaks, another strap kind of takes over for that strap. And so then multiple straps have to break before you fall out of the harness and plummet to your death if you're like hang gliding or something. So they say something has 4 fail safes. So each fail safe has to fail, all 4 of them have to fail before the person's actually in danger. They have 4 fail safes to keep that from happening. And this is for all over the place. It's for extreme sports, it's for like underwater diving, for going to space, anything where you have buildings, anything where you don't want stuff to fail and people to get hurt. So say they want at least one of the fail safes to keep working, so not to fail, bankrupt, so they want at least to keep working. And they say that every device has a 0.15% chance of failing. So we're looking for probably at least one works if there's four trials, there's four devices. So each device is going to be kind of a trial because each one has a chance of succeeding and working or a chance of failing. So we're going to do 1 minus probably of failing, right? Because this is the chance that they don't work. That's what we're doing with at least one. We always look at the opposite, and the number of power here would be how many backups you have. That's how many, the fail-safe devices. And here we know the chance of failing is 0.15, so we actually do 1 minus 0.15 to the fourth power. So this one will definitely get a decimal for it, because we're not even use fractions to do it, so I would expect a decimal from the calculator. So we do 1 minus 0.15, but that's going to be to the fourth power. So that's going to be the calculation to figure out, what are the chances at least one of these will stay working throughout. And if multiple devices work, that's great, because then we didn't have, more than one fail, or more than, too many fail. But at least one of them needs to succeed for us to be safe. So here we go. We get 0.9995, 99.95% chance that at least one device will work. And that's why fail-safes work really well, because even though one fail-safe has a 15% chance of failing, the chances that all four fail is really slim. Because that's less than, this is the chance that at least one of them works. The opposite would be like 0.0005% chance that they all four fail. So that's why we use backups. It's a good way to do that. And so this is at least once. Again, they're going to look for at least one to keep working. They're going to look for at least one right answer, at least one good roll. And that's when you use that at least one formula. And again, this is only going to be brought up in situations where we have independent events. The formula for dependent is a lot more calculated, a lot more frustrating. You have to sit there and calculate the probability for each separate part. So we're not going to worry about it unless it's independent. Okay, so that's 7b part 1. We'll finish 7b part 2 and then later. Part 2 basically will look at OR probabilities, which are a little bit different. We're looking, instead of saying do two things and they both have to work, we're going to look at something else. So this is, again, probability. It's all about counting the number of good options over bad. This is just kind of a faster way to do that. So doing the whole thing at once, you can kind of count each part and then multiply those together. That's the method. Hopefully that made a lot of sense. And again, like always, don't forget to ask me if you have questions about the homework. There's the Ask My Instructor button in my math lab. Great way to reach out. So keep using that.